The origin of inertia. Why do objects resist changes in motion? This is one of physics' deepest mysteries. When you push an object, it resists. This resistance to motion change is inertia, but where does it come from? Let's start with the basics. What exactly is inertia? Inertia is the property that makes objects resist changes in their state of motion. Push a box with force F, and it accelerates, but it doesn't want to. Something inside resists. Newton's second law. Force equals mass times acceleration. But what is mass really? Mass is the quantitative measure of inertia. More mass means more resistance to acceleration. We can rearrange to get mass equals force divided by acceleration. Mass is literally the resistance factor. Here's the mystery. Why does having more mass mean more resistance? What's happening physically? Historically, physicists treated inertia as simply fundamental and unexplainable. Newton treated mass as an intrinsic property of matter, something that just is, with no deeper explanation needed. For 3 centuries, mass was just a number you measured and plugged into equations. End of story. But this felt unsatisfying. Surely there must be a deeper reason why objects resist motion. Ernst Mach proposed a radical idea. Inertia comes from distant matter in the universe. Mach proposed that when you accelerate an object, you're actually accelerating it relative to all the distant stars and galaxies. The key insight is that inertia isn't intrinsic to the object, but arises from its relationship to all other matter. When you try to accelerate a ball, somehow all the distant matter in the universe resists, creating inertia. Mach's principle was philosophically appealing, but lacked a concrete physical mechanism. How do distant stars exert this influence? Einstein was deeply influenced by Mach's ideas when developing general relativity. In general relativity, mass curves spacetime its. This curvature affects how objects move through space. Einstein's field equations. The geometry of spacetime is determined by the distribution of mass and energy. An object in freefall isn't being pushed by a force, it's following the straightest possible path through curved spacetime. General relativity describes how gravity works, but it still treats inertial mass as a given quantity. The mystery deepens. Modern particle physics offers another perspective through the Higgs mechanism. The Higgs field permeates all of space. Particles acquire mass by interacting with this field. The mass of a particle equals its coupling strength g to the Higgs field times the Higgs vacuum value versus. The Higgs vacuum has a value of approximately 246 giga-electron-volts. This sets the scale for particle masses. In conventional units, this is about 4.4 times 10 to the minus 25 kilograms. The electron couples very weakly to the Higgs field, giving it a tiny mass of 0.511 mega-electron-volts. The top quark couples strongly, giving it a huge mass of 173 giga-electron-volts, about as heavy as a gold atom. Here's the catch. The Higgs mechanism only explains the mass of elementary particles, like quarks and electrons. Most of the mass in ordinary matter, including your body, does not come from the Higgs field. So where does it come from? Modern physics reveals that empty space isn't empty at all. The quantum vacuum is a seething sea of virtual particles constantly appearing and disappearing. According to quantum mechanics, particle-antiparticle pairs spontaneously appear and annihilate in incredibly short times. Heisenberg's uncertainty principle allows energy fluctuations for short times. Delta E times delta T is at least h bar over 2. Here's a wild idea. When you accelerate an object, does it interact with all these virtual particles in the vacuum? For ordinary matter, most mass comes from the strong nuclear force. A proton contains 3 quarks bound by gluons, the carriers of the strong force. The up quark has a mass of about 2 mega-electron-volts, the down quark about 5 mega-electron-volts. Yet the proton has a mass of 938 mega-electron-volts. Where does this huge mass come from? The proton mass is 938, vastly greater than the sum of its quark masses, which is only 12. The answer is Einstein's E equals mc squared in reverse. the binding energy becomes mass. Einstein's famous equation works both ways. Energy has mass, and this energy is what makes up most of your body. An astonishing fact: about 99% of your mass comes from the binding energy of quarks, not from the Higgs field. Let's break down where the mass of a typical human actually comes from. Take a person with a mass of 70 kilograms. Where does this mass originate? About 69.3 kilograms comes from strong force binding energy, only 0.7 kilograms from the Higgs mechanism, roughly 99% from quantum chromodynamics and 1% from the Higgs field. This is profound. Most of your inertia comes from energy, not from intrinsic particle masses. Let's estimate the energy density of quantum vacuum fluctuations. The vacuum energy density scales as h bar c divided by wavelength to the fourth power. At the Planck scale, the smallest meaningful length, this gives an absurdly large energy density. The Planck length is about 1.6 times 10 to the minus 35 meters, incredibly tiny. This gives a vacuum energy density of about 10 to the 113 joules per cubic meter. But observations show the actual vacuum energy is 120 orders of magnitude smaller. This is the cosmological constant problem. Despite this mismatch, some physicists think vacuum interactions might contribute to inertia in ways we don't fully understand. Here's a strange prediction. If you accelerate, you'll detect thermal radiation from the vacuum. The Unruh effect says an accelerating observer sees the vacuum as a thermal bath of particles. The temperature you measure equals h bar times acceleration, divided by 2 pi c times Boltzmann's constant. For an acceleration of 1 gram about Earth's gravity, the temperature is roughly 4 times 10 to the minus 20 Kelvin. This is incredibly tiny, far too small to measure with current technology. Some theories suggest that this interaction with the vacuum during acceleration might be inertia itself. Several modern theories propose that inertia arises from vacuum interactions. The Heisch-Rueda-Puthoff theory proposes that inertia comes from electromagnetic zero-point fluctuations. When you accelerate an object, it experiences asymmetric pressure from vacuum fluctuations, creating resistance. The theory aims to derive Newton's second law from first principles using quantum field theory. One prediction is that inertial and gravitational mass should be exactly equal, which matches observations. However, this theory remains controversial. Many physicists are skeptical of its mathematical foundations. A key experimental fact: inertial mass always equals gravitational mass. Drop a heavy and light object in vacuum, and they fall at exactly the same rate. Why? Inertial mass, which resists acceleration, always equals gravitational mass, which responds to gravity. This has been tested to 1 part in 10 to the 15th using precision torsion balance experiments. This remarkable equality hints that inertia and gravity must be deeply connected at a fundamental level. Let's calculate what happens when we accelerate a single proton. A proton has a mass of 1.67 times 10 to the minus 27 kilograms. Apply a force of 1 piconewton, that's 10 to the minus 12 newtons, for 1 nanosecond. Force is 10 to the minus 12 newtons, time is 10 to the minus 9 seconds. Acceleration equals force over mass, giving about 6 times 10 to the 14th meters per second squared. This acceleration is 60 trillion times stronger than Earth's gravity, yet the proton still resists. The velocity change is about 600,000 meters per second, or 0.2% the speed of light. Even at these tiny quantum scales, inertia is real, measurable, and demands explanation. Here's a question. If vacuum interactions create inertia, why don't we feel constant drag? The answer is subtle. Inertia doesn't resist motion itself, only changes in motion. At constant velocity, you don't experience any inertial resistance. You're in an inertial reference frame. Only when you accelerate do the vacuum interactions become asymmetric, creating the sensation of inertia. Does the large-scale structure of the universe affect local inertia? The observable universe contains about 10 to the 80 protons. Could their collective influence create your local inertia? The number of protons in the observable universe is approximately 10 to the 80th power. Interestingly, the gravitational parameter gm/r for the universe is roughly c². This remarkable coincidence might hint at a deep connection between inertia and cosmic structure. Is this just coincidence, or a profound clue about where inertia comes from? General relativity predicts that rotating masses drag spacetime with them. A rotating massive object literally drags spacetime around with it, an effect called frame dragging. The dragging angular velocity scales as g/c²r³, where j is angular momentum. This was actually measured by NASA's Gravity Probe B satellite in 2011, confirming Einstein's prediction. For Earth, the effect is tiny, about 39 milliarcseconds per year, but measurable with precision gyroscopes. This demonstrates that spacetime itself has inertia. It resists being twisted by rotating matter. In quantum field theory, particles are excitations of underlying fields. A particle is just a ripple or excitation in a quantum field that fills all of space. From this view, mass is the energy cost of creating and maintaining the field excitation. The energy of a particle satisfies E² equals momentum squared, c² plus rest mass squared, c⁴. Inertia becomes the field's resistance to having its configuration changed in spacetime. This connects deeply to Lagrangian mechanics and the dynamics of fields propagating through space. A practical question: how do we actually measure inertia experimentally? We measure inertia by applying known forces and measuring the resulting acceleration with sensors. Modern accelerometers use microelectromechanical systems to detect tiny accelerations. They can measure accelerations as small as nanometers per second squared. That's 10 to the minus 10 times Earth's gravity, incredibly sensitive. Despite all our progress, fundamental questions about inertia remain unanswered. First question: why do inertial and gravitational mass match so precisely? Is this a deep law or a coincidence? Second, is inertia a local property of matter, or does it depend on distant matter throughout the universe? Third, could we ever modify inertia or create inertia-free states? This would revolutionize technology. Fourth, how does classical inertia emerge from quantum field theory? The connection isn't fully clear. These questions surround our understanding of inertia like unsolved mysteries waiting to be unraveled. Understanding inertia has practical implications for future technology. Inertial navigation systems use accelerometers and gyroscopes to track position without external references. Modern inertial navigation can maintain accuracy to within 1 meter per hour of travel. LIGO detects gravitational waves, which are tiny ripples in spacetime that affect inertial frames. Inertial confinement fusion aims to create incredibly high-pressure plasmas to achieve controlled nuclear fusion. If we could manipulate inertia, it could revolutionize space travel, allowing for faster-than-light travel or more efficient propulsion systems.